I don't remember what we were doing. I know what he wants us to do, but I don't remember. I was like,
okay, guys, so let's look at your new handouts. We are going to do a little math today. I know. Okay. So let's take stock of where we are, where we're going. Chapter 2 was about limits.
He said that if you guys came in late, to grab a sheet over there.
Oh yeah, they're right up here on Luke's desk. Chapter 2 is about limits. Limits provide the foundation for the other three big ideas in calculus. The first, or I guess the second then big idea, is the derivative. What we'll be doing for the remainder of the year is applying derivatives to actually have a purpose. So we've pretty much just calculated them and used them to find slope, and that's about it so far, right? We'll do a couple other things that previously have only been calculator skills for you with derivatives. We'll also use them to help us classify functions and solve some physics and other application problems. Yes. Sorry? Okay, so there's a big wall of text on your front page just because I was anticipating this being a video, just the way the schedule worked out. Here we are together. Okay. What we're going to look at in the first couple sections is an application of tangent lines, specifically horizontal tangent lines. No, why? Because think, if the slope of a function is 0 at some place, it's very likely, not a guarantee, but it's very likely that that place is an extreme value. What were extreme values from the first semester? Maxes and mins. And then using a function's derivative, remember we said that tells us about the slope. Knowing the slope would also tell us where the function is increasing or decreasing, which is something we used a calculator to help us with, or something we just used a sign chart to help us with in pre-calc. Now we can actually prove it using derivatives. So yeah, that's what we're going to spend the first section or two looking at: increasing, decreasing, and extreme values. So I want you to look at these two graphs at the bottom of your page, and I want you to list all the extreme values on both of them. I want you to look at these two graphs and list the extreme values on both of them. If it helps, they are built from the same function. Graph A just has a restricted domain. Someone give me an extreme value on the first one and tell me if it's a max or min. A tip. Is that a max or a min? And would you call it local or absolute? Have we talked about that in our class? I honestly don't remember. I honestly don't remember. Have we talked about localness? Or we have? Okay, I'm getting people saying yes and no.
Not in this class, but we did.
Okay, in last year? Okay. So how about he said there's a min at 0, or sorry, min, how about min of 0 and x is 0? And we said it was an absolute. And I agree, that is the absolute minimum. It is the lowest point overall on the graph. Give me another one. -2. Tell me what it is. Local absolute. And again, I agree. This would be the absolute maximum because it is the highest point overall on this graph. And what about this other endpoint over here? Yeah, I call that one a local. In its nearby area, it is the highest point, but it's not the highest point overall. So we'd have one more here. How about on the second one, where the domain was unbounded? Someone different. Luke.
0, 0.
Okay. I agree. It is the absolute minimum. It's the lowest point overall. Would this graph have a local or an absolute maximum?
No.
No. It just grows forever.
He didn't even hear it.
Let's turn the page. Okay, remember the intermediate value theorem? And I warned you there's like 4 big theorems in calculus. Here's the second one. This one's the extreme value theorem. Because it's extreme. No, it just tells you about maximum. Please note, there are 2 conditions for the extreme value theorem to be applicable. A function must, 1, be continuous, and 2, you must be looking at a closed interval. If you are looking at a function that is continuous on a closed interval, you can guarantee there is both an absolute maximum and an absolute minimum in that interval. This theorem only applies if you're looking at a closed interval. What does the word closed mean?
Well, there's boundaries on
What? It is not infinite when you got brackets, when you got solid endpoints. So that would be something like bracket A, comma. Yeah. She did go, it's closed, and I was like, well, these brackets are parentheses, you know? You kind of hard motion there. So it's kind of like the IVT, right? You got, for the IVT, it was just a continuous function on a closed interval. This one's continuous function, closed interval. So then, I got a graph here. Notice we got a couple open points. There's a discontinuity in there. What do you think? Is there an absolute maximum on this graph? It's not continuous. Now, be careful. That just means we can't use the theorem. So let me clear that up real quick. For the theorem to be relevant, you have to meet both conditions. However, you can have maxes and mins even if a function does not meet the conditions. It's just the theorem's only relevant. You meet those 2. I've killed her. I've done it. That's it. That was too much math. We were good until that point. Doesn't matter. So, is there a definite highest point on this graph? What do you think? Yes or no? No, there's not. This open point looks like it should be the highest value, but because it's not included, how do you actually get a y value there? You don't. Why not? Because the highest value is at an open endpoint. So the function doesn't actually exist at that point. How about an absolute minimum, though? At D, yeah, there is an absolute minimum at D, even though the function is discontinuous. and we use the extreme value theorem to guarantee the existence of a max or min on this graph. See a lot of people shaking their head. Why? Not continuous. It's not continuous, and that's a good point, Daphne. The left endpoint is not a closed interval either. It'd be an open endpoint on the interval. Okay, let's turn the page. Last one for today.
Oh, I like that.
Okay, so I said one of the primary ideas in the first couple sections is extreme values. We got two big ideas here. One, if you're looking at a closed interval, not infinity to infinity, when you're looking for maxes and mins, make sure you check the endpoints. Not just the places where the graph is horizontal. Make sure you check the endpoints as well. Second thing, if you don't have endpoints, or maybe they're just not extreme values, the only place where you could find a max or a min is if the derivative is 0 or if the derivative doesn't exist. So basically, you need some place where there's a horizontal tangent, like right here or like right here, or some place where the derivative doesn't exist. I'll give you a visual in our example here for that one. Note, I bolded this for a reason. Note, these alone do not guarantee the existence of an extreme value. For example, how about the function x cubed? Let's think about what the function x cubed looks like. Kind of looks like this, doesn't it? The function x cubed has a horizontal tangent at the origin. Would the origin be a max or a min? It would not. Nah, you get the point. Not extreme. So the actual definition of an extreme value is more rigorous. It's a point where the function changes from increasing to decreasing, or vice versa. So I'll show you how we analyze a function for that. So we got a weird function for this one. It's the cube root of x squared, which just let's get a visual for that. Let's sketch that real quick. So kind of like the absolute value function, but not straight lines. It kind of looks almost square root-ish going off. But tell me about this point. What do you know about this point at the origin? Well, it's an absolute minimum. Sure, yeah, it's a cusp. No, that would be a cusp. That would be some point where the derivative does not exist. So that's what we're going to find analytically. Sorry? Sorry? Just horizontal. Because, well, think about a vertical. I mean, I guess the first thing that comes to my mind would be the cube root function, which I didn't do a great job of drawing it here, but the cube root function does have a vertical tangent right at the origin, but it's not a max or min. And like, a place where you got a vertical tangent is where you got like rapidly increasing y's, so I don't think that could be an extreme value. Okay, so if we're looking for extreme values, remember we got to test three things. We have to test the endpoints, which in this case we were given endpoints. We won't always be. Sometimes we will be. We also need to test wherever the derivative is 0. That could be a max or a min. And we also need to test wherever the derivative does not exist. Those are also locations where we could get extreme values. What do you say we actually do the endpoints last, just because everything else is going to fall in the middle? Is that okay? I know I put them as number 1, but... So let's take the derivative of this function. Let's check out where's it going to be 0, where's it going to be undefined. So what would the derivative of this function be? Someone who hasn't helped me yet. Someone who hasn't helped me yet. What would the derivative of this function be?
It would be 2/3.
Someone who hasn't helped me yet. I appreciate it. I just want to make sure everyone's involved. Madeline. Love it. If we needed to clean this, now let's clean this up a little bit so it's nicer to look at, nicer to solve. How about let's use that negative exponent rule. And then let's also maybe switch it from exponent to radical form. Maybe. Yeah, your call. Will this function ever equal 0? Is there any value you can plug in for x to make this equal 0? Nope. You don't buy it, set it equal to 0, try and solve. If you have, now you don't have to do this, you can just straight out claim it will never equal 0. Multiply both sides by the denominator. You wind up with 2 equals 0. Well, that's just factually incorrect. So that's not going to happen. So there are not going to be any of these for us to look at. Are there any x values which would give us a place where the derivative does not exist? At x equals 0. If you plugged in 0 in that x, you have 2 times 0 in your denominator. If your denominator zeroes out, you have a place where it's undefined. So this happens when x equals 0. Any place where the derivative is 0 or undefined is called a critical point. I did not get this in there somewhere as your vocab, and I apologize. So I wrote it. You could probably try and squeeze it into the summary lines down there or something. The best way I can summarize a critical value or a critical point is it is a candidate that could be an extreme value, but it might be, it might not be. Remember, we said for something to be a max or a min, the function has to change from increasing to decreasing or vice versa. Critical points, or critical values, are just where it equals 0, where it's undefined. So, for example, again, the cube function has a critical value. It just simply does not have an extreme value at 0. They might be extreme values, they might not be. So that thing we just found, that's a critical point. Critical value. Okay, so I think we're ready. Sorry, did I go too fast? So we need to finish the problem. I just needed to give you this definition. Waiting. Sorry? Endpoints can be extreme values. Endpoints are not critical values. So we haven't really finished this problem yet. Okay, you may remember we made some sign charts in pre-calc. Sign charts help us with derivatives and increasing and decreasing too. Let's see, this function in particular we were told to look at from -2 to 3. And we only found one critical value in the interior. It was at x is 0. When we start, I'll keep track of 3 things on my sign chart. Once you get good at it, you really only need to keep track of 2 things. We're going to keep track of x values. I'm going to keep track of the sign of the derivative, which then tells me something about the original function. So, just like last semester, we need to pick our favorite number in between the numbers that are already on the page. So what's your favorite number between -2 and 0? -1. Okay, cool. We're going to take that and let's plug that into the derivative. And I don't care about the number. I just care it's going to be positive or negative. So if I put -1 in here, am I going to get a fraction that's positive or negative? Negative. If the derivative is negative, what does that tell you the original function is doing? Decreasing. What's your favorite number between 0 and 3?
1.5.
Same thing, you plug it in, we're going to get a positive or a negative fraction. Positive, so what's the original function doing? Increasing. So I don't know about you, but I think this tells me that 0 is not only an extreme value, it's probably going to be a minimum. The function decreases until 0, and then it increases afterwards. To finish, we need some y values. What's up? Okay. We need some y values. So let's evaluate all of them. Don't forget the endpoints. Here's where the endpoints come into play. So this would be where we punch back into the regular function. Which, now 2 of these are going to be irrational numbers. So if it involved irrational numbers, probably. If it did not involve irrational numbers, probably not. Yeah. So I know you know how to push buttons on a calculator. And so the last thing to do is to decide which of these are local, which of these are absolute. Remember, you only have to, well, yeah, let's decide local and absolute. So this left endpoint would be a local maximum. The function starts somewhere and then decreases for a while. But I know it's local because on the other side is a higher point. So I'm sure you're about out of room, but we'll just try and squeeze this in here real quick. And then our last one is also absolute. What questions do you have for me? Okay, for tonight, there is a video. It is 9 minutes long. It is just another problem exactly like this. Well, okay, it's not exactly like this. The only difference is it does not have a bounded domain. It goes from negative infinity to positive infinity. So for tonight, all I want you to do is to watch that video, and then tomorrow, I'll give you time to work on both assignments because, to be frank, they're both pretty short, and I probably could just combine this into one section. Cool? Sweet. For tonight, there's a 9-minute video. It's another problem similar to this one. It's an unbounded domain instead of a bounded domain. And then tomorrow, I'll give you time to work on both worksheets because they go pretty quick.